Welcome to Unit 11, Video 4, Colligative Properties. By the end of this video, you should understand how and why non-volatile solutes change the boiling point and the freezing point of water. You should know how to determine the Van Hoff factor for a solution. And you should be able to perform calculations relating to boiling point elevation and freezing point depression. Colligative properties are properties of a pure solvent that change when a solute is added. So in other words, they're properties of, say, the solvent water that change when something like NaCl is dissolved in it. There's a lot of colligative properties. The ones that we're going to look at in this class are vapor pressure. Vapor pressure decreases when solute is added to a solvent. Freezing point, this also decreases when solute is added to a solvent. Freezing point depression is something you should be really familiar with, especially this time of year. When we, quote, salt the roads, that means that calcium chloride is laid down on the roads as a solute, which dissolves in the water on the roads and lowers its freezing point, keeping the roads from freezing. Boiling point is another colligative property we'll look at. Boiling point increases when a solute is added to a pure solvent. It's important to note that colligative properties do not depend on the identity of the solute, only the amount. So it doesn't matter what salt you're using, it only matters how much of it you're using. Let's look first at vapor pressure reduction. Recall that vapor pressure is the pressure of the vapor above the liquid in a closed container. Substances that evaporate easily will have a high vapor pressure. When we add solute to a solvent, the solute particles will prevent particles from escaping the surface of the liquid. This will decrease the rate of evaporation. Here, if you look at the closed container on the far left labeled A, we have an equilibrium between liquid and gas. However, if you add a solute, here the solute is glucose, you'll notice that the rate of evaporation has decreased and the rate of condensation has remained the same. When a new equilibrium is established, as you see in frame C on the far right, there's fewer particles in the gas phase than there were before. The amount of vapor has been decreased. Therefore, the vapor pressure has been reduced. Looking at this graphically, here you see vapor pressure of water graphed versus the mole fraction of water. Mole fraction is a form of concentration that we're not going to deal with in this class, but you'll notice that the vapor pressure is highest when we have pure water. But as the amount of pure water decreases, notice this scale goes backwards here, and the amount of solute increases, our vapor pressure will get lower and lower. Let's turn now to boiling point elevation. Recall that the normal boiling point is the temperature at which the vapor pressure is equal to 1 atm. Well, in the previous slides, we stated that the addition of a solute will lower the vapor pressure of the liquid. Therefore, it will elevate the boiling point. In other words, the temperature at which the vapor pressure is equal to 1 atm will have to be higher. Yet another way of saying this is that you'll have to add more heat to get the vapor pressure to equal 1 atm and initiate boiling. Boiling point elevation is used to make antifreeze and coolant. So this bottle here is a bottle of antifreeze and coolant. You pour this into the radiator of a car, and it will raise the boiling point of the water in the radiator of the car. Therefore, it will be able to take on more heat before the water in the radiator starts to boil. It prevents your engine from overheating in your car. Let's look at a phase diagram that represents the difference between the phases of a pure solvent and the solvent with solute added. Notice the purple line here represents the pure solvent. When solute is added, we get the blue line. Notice that the liquid vapor line has moved outwards, and the solid liquid line has also moved outwards. By addition of the solute, notice if we follow our 1 atm line across, here's where our normal boiling point used to be. Now with the addition of solute, our normal boiling point is here. We have raised the boiling point. We can calculate the magnitude of the boiling point elevation by using the equation below. In this equation, delta T is equal to the change in the boiling point, or the change in the temperature of the boiling point. I is equal to the Van't Hoff factor, which we're going to talk about in a bit. The Van't Hoff factor corrects for the fact that some substances put more particles in solution than other substances. Kb is the molal boiling point elevation constant. This is unique to the solvent used, and you'll be given this constant. And finally, small cursive m, you may recall, is the molality of the solution. You might want to consider why we use molality here instead of molarity. Let's look now at freezing point depression, and then we'll come back and practice some calculations. Recall that the freezing point of a substance is the temperature at which the liquid phase and the solid phase have the same vapor pressure. Again, since we know that solute will lower the vapor pressure, this lowers the freezing point. In other words, the temperature at which the vapor pressure of the liquid is equal to the vapor pressure of the solid is lower. Put yet another way, you need to cool the solution more to get it to freeze, to get the vapor pressure of the liquid to equal the vapor pressure of the solid. This is made use of, as we said before, when we salt the roads. When we pour rock salt on the roads, it lowers the freezing point of the water on the roads, keeping them from freezing. We can calculate a new freezing point exactly the same way as we did a new boiling point. The equation is exactly the same. The only difference is now we're using the Kf, the molal freezing point depression constant. And again, you'll be given this value. So before we can perform calculations, we need to define what the Van't Hoff factor is. That's the small I in the equation. So as we said, the magnitude of the effect on colligative properties is dependent on the number of particles in solution. So when we dissolve something like glucose in solution, we know that glucose, for every one particle of glucose you put in water, you get one aqueous particle of glucose. So if you put 1 mole of solid glucose in water, you will get 1 mole of dissolved glucose particles. However, as you should recall, when we put ionic substances in water, they dissociate. So if I put 1 NaCl particle in water, it will dissociate into an Na plus and a Cl minus ion. This produces 2 particles in solution. If I put 1 mole of NaCl in water, I will get 2 moles of aqueous particles. Likewise, calcium chloride dissociates into 3 particles, 1 calcium and 2 chlorides. Therefore, calcium chloride of these 3 substances will have the largest effect, assuming you add the same amount of each. Interestingly, calcium chloride is what we use when we salt the roads. It's not NaCl that's used in rock salt, it's calcium chloride. The important thing to remember is that more particles will cause a larger effect. We can quantify this using the Van't Hoff factor. This is the relationship between the moles of particles in solution and the moles of particles dissolved. Here's a table showing Van't Hoff factors for some common substances. Let's look first at the column that says expected. Notice that for non-electrolytes, we always get a Van't Hoff factor of 1 because non-electrolytes do not dissociate into more than 1 particle. For NaCl, we get a Van't Hoff factor of 2 because we get 2 ions. MgSO4, again, 2 ions, an Mg2 plus and an SO4 2 minus. MgCl2, we get 3, an Mg2 plus and 2 Cl minuses, and so on and so forth. You'll also notice that sometimes the measured value is slightly lower than the expected value. It turns out that at any given time in solution, some ions are actually paired and not completely dissociated. This is called ion pairing. This results in a slightly lower number of particles than we would expect in solution at a given time. We can always, unless I tell you otherwise, you can always use the expected Van't Hoff factor. If you need to use the measured Van't Hoff factor, you'll be given that value. Now that we know all the parts of the equation, let's put them together and try a problem. This question asks us to calculate the freezing point depression of a solution of 2 moles of ethylene glycol in 0.5 kilograms of water. I know that my equation is delta T equals I times Kf times the molality. Before I go any further, I'm going to have to calculate the molality of this solution, which you should know is the moles divided by the kilograms. In this case, I have 2.0 moles and I have 0.500 kilograms. Therefore, I have a 4.0 molal solution. Now, coming back up to the top, I know that my delta T is going to be equal to the Van Hoff factor. So ethylene glycol, C2H6O2, is made up entirely of nonmetals. So it must be a covalent molecule, not an ionic compound. Therefore, it does not dissociate in water, so my Van Hoff factor is 1. Kf here is 1.86, I'm given that in the problem, and I just calculated my molality to be 4.0. If I do this math, I find that my freezing point depression is 7.4 degrees Celsius. Notice that I have not used the Van Hoff factor to limit my sig figs here. Since it's a predicted value, we can assume it has infinite sig figs. So this tells us that if we add 2 moles of ethylene glycol to 0.5 kilograms of water, our freezing point of that solution will go down to negative 7.4 degrees Celsius, since its original freezing point was 0. Here's some problems to try on your own. Pause the video here and see if you can answer these 2 questions. Notice in the first problem you're given the Van Hoff factor, but in the second problem you should use the predicted Van Hoff factor for CaCl2. Welcome back. Here's what you should have gotten. That brings us to the end of this video. Let's review our goals. First, we looked at how and why non-volatile solutes change the boiling point and freezing point of water. Then, we learned how to determine the Van Hoff factor of a solute by determining the number of particles the solute puts in solution. And then we performed calculations related to boiling point elevation and freezing point depression.